All right. Welcome to the very last talk of PLDI. Thank you for being here. This is my talk. So this is a joint work with Guido, my advisor sitting right here in the front, and Pascal, who should be looking at me through the camera over there. So let me tell you a little bit about what these fundamental algebraic laws are. But it's not me who will tell you what they are. It's instead Guy Steely who will tell you. So in 2010, so that's 14 years ago, he did this keynote at Strange Loop. And he was telling, well, his advice about how to think about parallel programming. And he ends his talk by saying, everything else doesn't really work. You should just think in terms of algebraic properties at the end. But that was just 14 years ago. By then, we learned that even more properties are crucial for verifying systems, checking these things, distributive, absorption, blah, blah, blah. And these things actually happen more than in just parallel programming. So compilers use them. Abstract models use them in concurrency. So CRDTs being quite hot, essentially being a semi-lattice, which require these algebraic properties. In implementations and in academic work of stream processing, of course, type classes, and in standard libraries. So, for example, in Scala or in D, I guess, whenever you want to fold over a list, they tell you, well, in parallel, they tell you, please make sure the function you give me is associative. But they never actually check that because they really can't. I should say, if any of your work, also your work, people watching me in the stream, if any of you use these things, please let me know, and I'll happily put your paper in my slides. Free advertisement. All right, so now hopefully you've convinced that these things are useful, they're everywhere. And we want to automatically verify them. Because, well, we can hand wave our way. These things are good, but no one really believes us. We can handwrite a proof, so that's if we kind of write a simple paper. But you might pull this face. But worst of all, if you mechanize your proof, then it's quite annoying and tedious. But reviewers like that stuff. They don't like this stuff. So ideally, you would just automatically verify these things. This way, you and the reviewer of your paper are happy. So let me show you how our tool kind of automatically verifies some of these properties. I'll just take a very simple example, just for the sake of these slides, and it's this screenshot from Piano's paper from 1908. This plus that you see all the way down, this is abusive notation, or operator overloading, as we call it in programming. The plus on the left-hand side is addition, and the plus on the right-hand side is the successor function. So we will convert this into code. We choose Scala because this is the language we target. So we create an enum with our case classes. And then we convert the code into, well, the math into code. We get this. But of course, we want to do algebraic properties. So we have to say which algebraic properties apply there. And we add them to the types. So we say addition is a recursive function that has properties of commutative, associative, takes two numbers into another number. And that's the definition. But what do we want to do with it? We want to kind of create a proof tree. So we're all kind of familiar with proof trees. So this is what they look like. But in parts, these are the parts we're interested in. So in yellow is the usual typing context. The goal is the blue. The set of equalities or lemmas or the psi theorems that we know are in green. And we also track disequalities. So things that we know are not true. I'll come back to this later because this turned out to be an interesting insight that we have in our tool. And the problem right now is how do we find these trees automatically all by ourselves? Our tool follows this kind of very simple but kind of powerful cycle, which is, first of all, it looks at case analysis to generate equalities and disequalities. So which paths we take, which paths we don't take. We then apply some kind of rewrites. So the stuff that we know, maybe that some other function is commutative, we can apply that. Oh no. OK. Then we kind of, after exploring some of these rewrites, we select some interesting ones. More on this later. And then we kind of do some kind of symbolic execution, and we restart until hopefully we've proven what we wanted to prove, or we get stuck somewhere, or we prove that we cannot prove. Well, we show that we cannot prove, we don't, yeah. But overall, this whole kind of cycle of the main proof is not just by itself, because rarely do we ever prove things without knowing other stuff. So in the global picture of things, there is these things called lemma, which we have to explore, well, generate them somehow. But we also have to prove that they hold true before we actually move on into the proof that we want to prove. So the general structure of the presentation is I show you the big picture, just like the previous slide, then I will go down a little bit more into details until hopefully the time runs out and then there's questions. So lemmas, let me show you the two lemmas that we, the two shapes of lemmas that we found most interesting to generate. First of all, distributivity. We found distributivity to be quite important because it allows us to just reorder things, right? I want to reason about G before I want to reason about F, or the other way around. And this is what distributivity gives us. But of course, we have to know what these F and Gs are inside the code. As an example, let's take the multiplication that uses addition. So these are over piano numbers, typical stuff. We will not, for example, conjecture that multiplication distributes over list concatenation, because they have nothing in common. Instead, we will just try to look at definitions that use each other. And this will hopefully give us some idea about where distributivity could be used and where the proof of distributivity could be easy to generate. So in this case, we find that multiplication and addition use each other. So we conjecture some distributivity laws, and then we prove some of them. And the ones that pass, in this case the first two, we put them in our context. The other ones we discard them. The other kind of lemma exploration we do is called generalization. Don't read the code, there's a lot of stuff. I will zoom in on the interesting things in a bit. The idea there is I want to take my function, I apply it to all possible unfoldings of the constructor up to one level, two levels, however many you want, we just do one. And then you try to relate the output, the symbolic output, to the inputs. As an example, I will focus on one of them, this concat nil and nil being nil, concat being list concatenation. And there we see that there is some kind of a relationship between the input and the output. There's three kinds of relationship, or three questions we can ask. In red, I'm asking, is concatenation giving me nil because the first argument is nil? In green, it's asking me, is concatenation giving me nil because both arguments happen to be nil? Then I kind of generalize these, and I conjecture the lemmas on the right. And of course, in that case, some of them hold, some of them don't hold. I discard the ones that don't hold, and I keep the ones that do. Simple stuff, but quite powerful. So let me go back to this proof that we wanted to show that addition is commutative. So if you remember the definition of addition somewhere, this would be what we want to prove. The proof will always start with four things. So we have the goal, the typing context, equalities, and inequalities. For the sake of the proof, we will discard the typing context until it becomes relevant, and we will just look at the equalities and inequalities. Sometimes I might say disequalities instead of inequalities, but that's just, there's two conflicting terms. It's random. The first thing we do is we actually, let me go back, we do not prove this claim. We do not prove that addition is commutative. We rather unfold the definition and then we prove. This is kind of important. I'll tell you a little bit why later. The first part of the cycle, which you'll see on top, is that we first do case analysis. So Propel, the inductive theorem prover, sees that there are two case expressions on either side. And it just explores the four possibilities of the branches. And these are the four possibilities on top. And then, essentially, to complete the proof, you have to prove every branch. If you focus on this particular branch, just to see what happens, we can, so that's the focusing. Then we can apply everything that we know. In this case, we only know two things, which are these things in the green box right there, being the branches that we follow. We now apply the rewrite of, in which we follow the rules, and we end up with these four other ones. We also apply all the known lemmas. I haven't shown you these things, but here they are. So essentially, distributivity of successor and addition. And then we generate these things. Now, this is after only one step of going down the branch. This is way too much, because there's way many more steps later. So the question now is, which one do we pick? Which one look attractive? There we have to score the branches, so we have to conjure some sort of magic, or we can use a simple scoring function, which turned out to be quite easy. You can look at the paper for the details of this function, of how we actually score, and then we can talk about it later. And then we select the top n branches. In this case, this is the branch that we follow. Now you follow these, you apply the rewrites, the symbolic execution, blah, blah, blah. Then you reach this point, and here you have to use the inductive hypothesis. But we have no inductive hypothesis. We have nothing in the green. Except now the typing contexts come in handy, because according to the typing context, addition is commutative. So we can create the induction hypothesis out of the type, apply it, and we're done. And is this induction? Well, according to Propel, yes, it is, but modulo some kind of well-foundedness check. But the thing is, it falls out of the type. Then you're done. So that would be about the really nice system, the simple lemma generation. But I want to go back to this inequalities, because I've told you these are important, and this is some of the insights we found. For that, I'll just quickly skim through the proof of the fact that successor distributes over addition. Again, we pattern match. We follow one particular case. In this case, there should be a contradiction. How do we know? Because we simply see that B is both 0 and not 0. For those of you who attended my eGraphs talk on Monday, you would have seen the proof, the much longer proof to deduce that this is a contradiction if we did not track the disequalities. Essentially, we would have to apply 5 or 6 sequences of rewrites until we get some sort of reflexivity. To get an idea of how useful these inequalities, disequalities are, we took this commutativity proof, we turned off inequalities, disequalities, plotted all of the terms that come out of them, and this is the picture, very beautiful picture, I must say, that we get. In red are all of the useless branches that you would get rid of if you keep disequalities. The green ones are all of the fresh terms or new terms that you would not have explored if you disabled disequalities. So keeping disequalities allowed us to explore more things, more potential branches that could lead to a simpler proof. And if we disable them, then we're stuck proving contradictory terms. That was one of the insights. Of course, we evaluated this because we have to have an evaluation. We took the piano numbers and bit vectors as a first step. We compared it against, well, we collected about 43 cases that we wanted to prove. We compared them against Hip, Spec, and Zeno being inductive theorem provers, Cycle Q being a cyclic theorem prover, CVC5 and Vampire being SMT provers who are able to do induction. And then the two kinds of Propel, one with support for disequalities, the last one, and the one without, which is the previous to last. We performed better than all of them. Good for us. And in the case for disequality, we actually could not prove about 2 or 3 cases. In some other cases, such as the TIP benchmark, which is a benchmark for inductive theorem provers, their disequalities helped us to prove things faster, so we timed out on more cases. But we also did some more evaluation on divide and conquer algorithms, CRDTs, data flow engine operations, etc. All the juicy detail are in the paper with the numbers, because here we can't put numbers, there's too many. In conclusion, let me just summarize the insights that we got, which is that disequalities are very helpful. Please include them. Induction, well, your system is simpler if induction just falls out of it without having a special rule for it. The simple kind of conjecturing lemmas goes a really long way. Do not unfold definitions, just one layer is good enough in our case. And if you ever want to use progress, just make sure you only use the lemmas and the things which you have proven. You can use our tool. This is the website, and this is the concluding slide. If I may suggest a drinking game for you, every time you try to prove a simple thing using cock or lean or something, then please come to me. I'll give you a coaster for a glass, for like a shot glass, and then please take a shot every time you do that. It could be water. It doesn't have to be alcohol. Thank you very much, PLDI finishers. Enjoy your trip back home.
Okay, thank you for the talk. Very nice work. Do we have a question from the audience? Please go to the microphone.
And so, very cool project. Seems really interesting. I had a chat also with Guido and a short conversation about how you're planning to use e-graphs.
Yep.
And so I'm trying to do a very similar thing, right? But I haven't yet found what is an underlying logic to have this sort of like equational, symbolic only algebraic reasoning. So do you have an underlying logic?
In the paper, yes. So we have a really large formalism section.
Okay.
That is also simple, I must say.
And what kind of logic, more or less, is it?
Well, it's kind of simple constructive logic based on type theory.
Okay, yeah, it's very simple, like Hilbert style.
Kind of, yeah.
Yeah, thanks. Very interesting. I was curious about this lemma generation and exploration. How does that relate to Knuth-Bendix? Is it basically the same, or is it more or less expressive?
I think the generalization is actually pretty related. It might be more or less the same. Some older work explored this idea, and this generalization we kind of got more inspired from Zeno, which does something similar.
Okay, thanks.
Thank you.
Hi. So it seems like the examples you showed were properties that held across all of the total range of the inputs. Have you considered perhaps like a refinement system where a property holds for, say, half the domain of like the integers or something?
That's a very cool question, and I will give you the cool answer, which is that no, we have not. But since maybe something I should have mentioned is that we target just purely functional subset of Scala.
Mm-hmm.
And in my humble opinion, I think most of these refinements could be done via types.
Mm-hmm.
And then you can use some tools, which we actually saw in some talks about getting rid of these intermediary layers and data structures to kind of encode via your data type the refinement that you want, and then you kind of prove it over there.
Right.
Nonetheless, I still think there could be something that we could do inside of here. I just have to think about it.
Okay, yeah, thank you.
Yeah, thank you.
So a little bit along the same line, you might have an operator that is associative. It has a free identifier in it, but the associativity depends on some property of that free identifier. Is that possible to use in your tool?
I have a slide for this. I hope. Yeah, so I think maybe I hope this is something related. Let's see. So here I kind of show that addition is commutative associative. Then I kind of have this higher order operator called it's this thing. Zip with, which does kind of pairwise some kind of operation. And because these annotations are attached to the types, you're able to carry them around via higher order stuff. So for example, here in this zip with, I'm saying it's a function that takes a commutative associative idempotent function, then it lifts it up to another commutative associative idempotent function over the lists. Is this related? Was this okay?
I guess yes.
All right, thank you very much.
I'll also make
Yeah.
Well, I was going to ask a similar question to the last two, but maybe it'll turn into more of a comment, which is you mentioned in the very beginning these applications to, for example, distributed data processing or stream processing where you may need commutativity and associativity. And in that context, some previous research found that sometimes you have a commutative associative operator, for example, for MapReduce, but it's only commutative associative, assuming some extra properties on the input. So I think that goes back to the previous question, would be a very, very interesting thing to consider in your setting.
Yeah, which is why I kind of lured you with the free advertisement of the paper so that you can give me these examples and I can try to formalize them myself. Thank you very much.
Okay, very good. So do we have any other questions from the audience? If not, thank you all for sticking around for the last session, and let's thank our speaker.